So how are the homework problems over central limit theorem for sample means going? I got an email from you, Michaela.
I know.
Did you see my answer?
I did, actually, but I was working on organic chemistry.
Oh, you haven't tried it yet?
No.
Okay. Any questions? Don't act like it's going real good for you, because I know better. It's hard stuff, right? This section is tricky. There's a couple of problems that are a little bit harder to figure out how to do. Oh, there goes the siren. But let's see if you can do this one. This is the homework. All right, it says Thompson & Thompson is a steel bolts manufacturing company. Their current steel bolts have a mean diameter of 143 millimeters and a variance of 49. Pardon me for pausing, but that's a big bolt. 143 millimeters is 14 centimeters. That's like diameter of bolt, that big, right? So these are big bolts. Anyway, variance of 49. If a random sample of 30 bolts is selected, what is the probability that the sample mean would differ from the population mean by greater than 1.2 millimeters? Whew, what?
So do we need a square root of 49?
Hey, good point. It says, say hi to the camera. It says variance of 49. So that's been tripping some people up. When it says variance, that's different than standard deviation. How does variance and standard deviation relate? Standard deviation is the square root of the variance. So variance is standard deviation squared, right? So for this problem, it says the variance is 49. So what's the standard deviation? 7. Okay? Then it says the mean diameter is 143. So that's mu of x, right? The mean of individual bolts is 143. Right? Now, it says if a random sample of 30 steel bolts is selected. Okay, random sample of 30. I'm not talking about a single bolt here. I'm taking a sample of 30 of them and I'm computing the mean, x bar, from those samples. So how do I find probabilities for sample means? Okay, you got to change the standard deviation into a standard error of x bar by the central limit theorem. Good. So this is a central limit theorem problem. So on the test Friday, you have to recognize, oh, is this one of those central limit theorem problems, or is this a regular normal problem? Regular meaning if I randomly select one bolt, what's the probability of blah, blah, blah? Then you would use the standard deviation. But if it says I take a random sample of 30 of them, now I find probability for the mean of those 30. That's a central limit theorem problem. Yeah?
Are you going to say take a mean of 20, and that means that we have to use the normal one instead of the sometime one, because the 30 is one of the requirements you have to meet? Can you do that to us?
Yeah, that's a great question. You probably couldn't hear what he said. He's asking, would you try to trick us and say a random sample of 20 steel bolts is selected? What's wrong with 20? It's too few by the central limit theorem. Central limit theorem says that you have to have a sample size of at least 30 or what? A normal distribution. Does it tell us that bolts are normally distributed? Probably not. So, on the test, if I did put 20, what you would say is, I'm going to have to make the assumption here that the bolts are normally distributed. Otherwise, what follows is not going to be valid. But go ahead and work it. Right? Probably I wouldn't do that. And if I did, it was probably an accident. that I didn't think about. Oh, wait, that's less than 30. So anyway, back to the problem. What's the first thing you're supposed to do now to solve this problem? Draw a picture. Very good. So let's draw a picture. Actually, let me just put this up. I got room under here to draw the picture. Okay, so the central limit theorem tells us the distribution will be approximately normal. So I draw this normal curve. Where is this, by the central limit theorem, where is this going to be centered? He said in the middle. That's like a joke, man. Where's it going to be centered? In the middle. Yeah. But where is that? What number is that going to be? 143. Right? The central limit theorem tells us that the mean of the sampling distribution, which, by the way, that's what I'm drawing here, sampling distribution for n equal 30. Right? Sampling distribution of x bar for n equal 30. So the next thing I need to do is I need to draw my little dotted lines halfway down the hill to anchor the values so that I know what my scale is here. What is the standard error for means of samples of size 30? Here's the standard deviation. What's the standard error? And this is by the central limit theorem. Standard error of x bar is
Sigma over square root of n.
okay, sigma over square root of n. So they tell us that sigma is 7. So 7, I'll go ahead and write sigma over the square root of n, which is 7 over the square root of 30, which is go ahead and work it. I do it in my head, but I don't like to show off. You got it, Adam?
1.28.
1.28. Give me like 4 or 5 decimal places.
1.2780.
80. Okay. Everybody got that? All right. So that tells me that this dotted line is at what? 144.2. I'll put 3. On a picture like this, too much decimal places just gets in the way. I'm not going to be that accurate anymore. So I'm rounding here to 1.3. And so I add 1.3 to 100 to the middle, to 143. And then if I subtract 1.3, I'm at 141.7. So now I can draw what they want me to shade. And remember, you shade what they want the probability of. They want the probability. What is the probability that the sample mean would differ from the population mean by greater than 1.2 millimeters? So, probability that you differ by more than 1.2 from the mean. So what is that? What's 1.2 millimeters from the mean? 144.2 is 1.2 bigger than the mean. What's 1.2 less than the mean? 141.8. So when they say something like they did here, differ from the mean, they don't specify direction. That's plus or minus 1.2 millimeters. So here's the region I'm supposed to shade from the solid line to the solid line. Now give me a ballpark estimate of that. 65%. Where'd you get that? That's really good.
Because it's slightly below where the standard deviation should be.
It's going to be slightly less than the dotted lines, which the empirical rule tells us is 0.68. So he guessed 0.65, right? So my BP, my ballpark estimate, is 0.65. If I get a number pretty close to that, then I probably got it right. If I get a number way off from that, then I probably did a 1 minus thing, or I got something wrong. So to finish what I started to write here, this is 141.7 to 144.2. That's what I'm supposed to find the probability of. All right? Question?
That's 141.8.
Yep. Thank you. I was just seeing if you were watching. I looked over here and I got that number, but I should have looked over here. Question?
Further, it says greater than 1.2. Would that be the outside?
Yeah. He's got a good point. Now, does it matter? It says greater than. What if it had said greater than or equal? Does it matter? Hint, this is a continuous distribution. What's the probability of being exactly equal to? 0. So it doesn't matter. If it's a continuous distribution, it doesn't matter. You don't have to worry about it. But if it's a binomial distribution or a discrete distribution, then it makes a big difference. You have to pay attention. Now, is it strictly greater than or greater than or equal? All right. Okay, so now I think we're ready to go to the normal distribution. Oh, you know what?
Yeah, it's the outside.
I got this backwards. I got it the way I'm going to work it, but I shaded the wrong region, didn't I? It says differ by greater than 1.2. This is differing by less than 1.2. So is that the point you were trying to make?
That's what I was trying to
I thought you were trying to just say, do I include the line or not?
No.
Thank you. So, see, I was doing that just so you see that, yeah, things can be done wrong, and then you can catch the mistake. But that wouldn't have helped with my ballpark estimate either, because I'd still got a number close to my ballpark estimate. So I'm going to have to edit that as well. So now I need this, right? I need that tail, and I need this tail. And then I need to do what with those two tails? Add them together. Now, there's 3 ways you can work it from here on out. One is to find this tail separately, find this tail separately, add them. But by symmetry, what's going to be true? The 2 tails are going to be the same. So you could just do 2 times whatever you get from one of the tails. Or what's the third way?
1 minus the middle one.
1 minus the middle, which is this. So 1 minus that is what is probably going to be the easiest thing to do. Now, what's my ballpark estimate now? 0.35. If we thought it was about 0.65 in between, then 0.35 would be what the tails are. Right? So you can do it in your calculator any of those 3 ways. I'll write it up here this way. 1 minus normal CDF from 141.8 to 144.2. Mean 143. Standard deviate. What goes here?
7 over root 30, so you don't have to round.
The 7 over root 30. Don't just put 7. That's a really common mistake. Probably on the test, I would have part A, and I'd ask you about a single bolt. And then part B, I would ask you about a mean of 30 bolts. And you have to know that, well, the first one I put a 7. The second one I put 7 over root 30. So put 7 divided by square root of 30. And you got it. 0.3478. Okay? Does that match our ballpark estimate? Really close. Closer than we really usually hope for. Right? So even if my ballpark had been 0.30, I'd say, yeah, it's pretty close. Right? Okay, everybody good? This one kind of incorporates all of the little tricks. It uses variance instead of standard deviation, so you got to remember to take square root. It does the differ by whatever, and you have to figure out what the endpoints are. And then here it tricked me because I went in between instead of outside, but it's got all those little tricks built into it. All right? I don't think there's any on your homework for tonight that are harder than this one. If you can do this one, you can do all of them. Woohoo! All right. So guess what we get to do today?
Harder percent.
More of the same. The next section is really just more of the same. All of this is central limit theorem type problem for sample means. Today we will do central limit theorem for sample proportions. Remember we said there's a sampling distribution for any statistic that you could compute from a sample. Sample mean is a statistic. Sample proportion is a statistic. Anything else would also work, but we're only going to do these two. So we've done the mean. Today we'll do the proportion. All right? So sampling distribution for sample proportions. Dang it. Okay? This is section 7.3. And we will have a central limit theorem that's very similar to the last one that we did for means, but it changes accordingly. So rather than me take the time to write it all out, I'm going to put it on the board and then I will talk you through it. So the first thing is to define notation. X, remember when we did the binomial distribution? X was a random variable that counted the number of successes in a fixed number of trials. So now if I take a survey, let's say, and I ask people something like, well, from our survey, ask them if they're a smoker, right? If I count how many people in my sample say yes to that question, that's my X. X is the number of individuals in the population that have a certain characteristic, and capital N is the size of the population. So this is the population proportion, X over N. So what do you think the sample proportion is? It's the exact same thing, only instead of from the whole population, it's from the sample. So the sample proportion, we put a little hat on the P. So P hat is X over N, where now X is the number in the sample instead of in the whole population, and little n is the sample size, not the population size. So P hat is X over N. Now before I go to the central limit theorem, let's come over here on scratch paper and remember the binomial distribution. Right? You know there's a test Friday, right? And the binomial distribution will be on that test. So what is the mean of a binomial distribution? If X is binomial, the mean of X, which we also called the expected value of X, what is that? Don't you remember? NP. Good. N times P. Right? If I flip my coin 30 times, how many heads do you expect to get? I don't expect to get 0.5 heads. The proportion would be 0.5. But the number would be 15, which you get 30 times 0.5. Right? So it's just NP. Do you remember what the standard deviation of X is? This one was not so intuitive. And I just gave it to you right at the end of that class period. But you've had to do homework with it. Do you remember what the formula is for the standard deviation of a binomial?
Square root of NP minus 1.
Okay, does that look familiar? If it doesn't, that means you haven't started making out your cheat sheet yet. Get that on your cheat sheet, along with all this new stuff today. Okay, so that's binomial. P hat is just a binomial random variable divided by a fixed constant. So its mean and its standard deviation are going to just be divided by that same fixed constant. So the mean of p hat will be the mean of x divided by n. Divide this expression by n. What do you get? You get p. So np over n, which is p. Now what is p? It was on the previous slide. The population proportion. So what this says is, if I take a sample and I use that sample to estimate the proportion, that on average the mean of those sample proportions will be correct. It will average out to the correct thing that I'm trying to estimate, the population proportion. All right, so now sigma sub p hat, which I will denote as SE p hat, standard error of p hat, take this expression and divide by n. Okay, here's scratch paper. N times p times 1 minus p, divide by n. Well, hey, we had algebra to get in here, right? If I want to put this in inside of the square root with everything else, I got to square it as it goes in. Remember that? So this is equal to the square root of n p 1 minus p over n squared, all inside. Now what can I do with the n's? Cancel one of them, and I get square root of p times 1 minus p over n. So if this is true, if x is binomial, we know these things are true, then if we take the number of successes and divide by the sample size, we get the proportion of successes. It must have these two properties. All right? Now, just like when we did standard error of x bar, there's an n on the bottom of the fraction. What does that do for us? That's a very good thing. What does it do for us? It lowers the value if
Big samples.
big samples. So as n gets bigger, this thing gets smaller, which intuitively makes sense. The bigger your sample, the less error. This is the standard amount of error for a sample of size n. If n's big, you're going to have small error. You'll do a good job of estimating p if you take a big sample. That's what this says. Now, the central limit theorem tells us those two things, the mean and the standard error, in addition to the shape of the distribution. When samples are taken, when the samples taken are simple random samples, the conditions for a binomial distribution are met. The sample size is large enough to ensure that this ugly thing, I'll come back to that. If this is true, a normal distribution can be used to approximate the binomial sampling distribution of sample proportions. Okay, there's the shape part of the central limit theorem. We talked about the mean, we talked about the standard error, and what does it tell us the shape is? Bell-shaped, normal, right? Normal distribution. But now we have this if part. Remember, all theorems are if this is true, then. So here's the if part. If the sample is big enough that this is met. Now, when we did sample means and did central limit theorem, we had a similar thing. Do you remember what the sample size requirement was? What was the if part of the central limit theorem for sample means that we did last time? 30. As long as you have n greater than or equal to 30, or you have a normal distribution to start with, then central limit theorem kicks in. Well, here we don't have a normal distribution to start with. We got a binomial distribution. So we have to have the sample size requirement. Now, let's figure out what the heck this says. What is n times p greater than or equal to 5? What's n times p? That's the mean, right? And n times p, if p hat, here it is. If p hat is x over n, what's n times p hat? X, right? So it doesn't have a hat on it, but it's saying as long as your sample's big enough that you expect to get at least 5 successes. I expect X, the number of successes, to be greater than or equal to 5. So you have to have 5 successes in your sample. And what would this be? N times 1 minus P. If N times P is the number of successes, what's N times 1 minus P? Number of failures. So you have to have at least 5 successes and at least 5 failures in your sample. Got it? So if I take my coin out of my pocket and I flip it 10 times, would I meet this requirement?
Not necessarily.
No, there's no hat on it. And this is a subtle point, and I'm not going to get too picky about it on the test. But I don't have to get 5 in my sample. I have to expect to get 5 before I draw the sample. So what would my expected number of heads be in 10 flips? 5. And expected number of tails? 5. So I meet it, just barely. Right? But now, let's say I want to take... I know that in the population, the proportion of people who have diabetes is 0.01. I actually don't know what it is. But let's say 1% of people have diabetes. How big of a sample do I need to take in order to get 5? Not 1,000, but... How many, if I sample 100 people, how many would I expect to get? 1. So to get 5, I got to sample 500. Right? So the sample size requirement here isn't a single number like it was for means, 30. Now it's, well, it depends on how rare this condition is. If it's a rare thing like diabetes, 0.01, diabetes is not that rare, but then you need a bigger sample. If it's 50-50 chance, like flipping a coin, you can get by with 10. Right? Okay. So the if part, if it's met, then we can do normal distribution to compute probabilities. Okay, so all of that we did. So now we're ready to work a problem. I'll do one, we'll do it together, and then I'm going to cut you loose on working them yourself. All right, so here we go. It says, in a certain conservative precinct, 79% of the voters are registered Republicans. What is the probability that in a random sample of 100 voters from this precinct, at least 68 of the voters would be registered Republicans? So what are they giving us? It helps if you read, like on the test Friday, you're going to come in, you're going to read something like that, you're going to have test anxiety, and you're going to panic. Like, oh God, that's too much information. So then you just go back, read it again, start writing down what they give you. So the first number I hit is 79%. What are they giving me?
The expected number of Republicans.
Not expected number of Republicans. Probability, right? So what are they giving me in my formulas that I'm using? P. That's P. So this is what's given. P is, it's not 79, it's 0.79. So they're giving me that. And then I keep reading. Of the voters, blah, blah, blah. What is the probability that in a random sample of 100, what did they just give me? N. From this precinct, at least 68 of the voters would be registered Republican. At least 68. What are they giving me? X. X is 68. And then they want the probability that X is greater than or equal to 68. Well, since our central limit theorem we just learned doesn't deal with X, it deals with P hat. Let's get P hat. So this is what's given. Now I can say, well, P hat is equal to, what would P hat be? What's P hat? X over N. So X over N is, y'all looking at me like, 0.68. That one's easy. I can even do that one in my head. The next one probably won't be. It'll use some other n. But so this is exactly equal to the probability that p hat is greater than or equal to 0.68. What's the next thing we need to do? Check the assumption on sample size to see if we can use the central limit theorem. Do we have at least 5 successes and 5 failures?
Yes.
Yeah, we got 68 successes and 32 failures. So easily. No problem. So, next thing we need to do is compute the standard error of p hat. So the standard error of p hat by the central limit theorem is the square root of p times 1 minus p over n. Now, I know it's up here on the screen what the answer is, but make sure you know how to get that in your calculator, because it can be a little bit tricky with the parentheses to make sure you do it right. And if you don't match that number, then you know, oh, I must not understand how to do the parentheses. Megan?
Where did you put the 1 minus 0.79?
I was being in a hurry and seeing if I could catch you confused. She said, where'd you get 0.78? Well, I didn't. It should be 0.79. I was looking at the 0.68 probably above it when I wrote it. So it should, I wrote a 7. You know what the problem is? Multitasking. I can't think and write at the same time. That's really not a good thing. So 0.79 times 1 minus 0.79 over 100. Does that make more sense? And let's see, this is old. Let me erase it. Was everybody able to match that number? So what's the next thing we should do? Hint. Draw a picture. All right, draw a picture. So let me come over here. The central limit theorem we decided was met, so that tells us the shape of the distribution will be bell-shaped and symmetric. So I'll draw me a nice normal curve and center it at what? It's okay, I can wait. Where would this be centered? 0.79. The central limit theorem told us, I erased it to draw this, but it told us that the mean of p hat was the population proportion, which is 0.79. Now, halfway down the hill is how far away? You need to draw these dotted lines and get their values to anchor the numeric scale here so that your drawing is halfway accurate. 0.04 away, exactly. Right? So I'm not going to bother with the 073 on the end. For my drawing, 04 is good enough. So 0.04, that'd take me to 0.83. And then on this direction, it would take me to 0.75. So now I'm ready to look at what they want the probability for and shade it. Where do they want? They want 0.68. Where is 0.68? Well, it's that way from 0.75, right? But how far that way? Well, if this is 0.04, there's another 0.04, so that would be 2 standard errors would be 0.71. 3 standard errors would be 0.67. So 0.68 is darn near 3 standard errors away from the mean. Now, where do I shade according to what they ask? It says greater than or equal to, so I'm going to shade. Give me a ballpark estimate of the answer. 999, really close to 1, right? So my ballpark I'll say 0.99. And I'll bet you the answer is bigger than that even. Right? Because that's almost 3 standard errors out there, and I'm shading the whole thing. So now, how do I compute the probability? See, students at this point sometimes lose track of the big picture. Right? They're down in the trees, and right? But this is central limit theorem. The central limit theorem is what told me I could draw the picture like this. Since this is a normal distribution that tells me to find a probability from a normal distribution, I use what? Normal CDF function. Right? So normal CDF from what to what? 0.68 to infinity. Centered at, or mean of, 0.79 and standard error of 0.04073. And you need to, if you type in a number here, you need to keep lots of decimal places of accuracy, at least 5. What they'll tell you to do is to type that whole expression with the square root into that slot, which will eliminate any round-off error. So you can do it like this. Normal CDF, 0.68 to infinity, 0.79, and then just type that whole thing in. Square root, 0.79, 1 minus. But that's a big, ugly mess trying to do it all. So I actually, when I get to these proportion problems, I bail out, I compute that first, and then I type that number in. And the calculator has a lot of memories built into it. You know how to use the memory on your calculator? There's a little button down here that says STO, that's for store, and an arrow. So if you get a number on your screen like 0.04073, whatever, hit that button, store, and then the green alpha button, and hit the number 1, and you just put it into Y, because it has a green Y above the number 1. So memory Y has that number. Then you can just do your normal CDF and put Y there. And you won't have any round-off error. But like I said, it's not that big a deal. As long as you keep at least 5 places here, your answer will be accurate to 4 places when you get done, which is what they want. So you don't have to go to all that trouble. So what do you get as an answer? 0.9965 to 4 places, that's what it is? Yep, so our ballpark was around there, so looks good. Now, if I had accidentally shaded the wrong direction, my answer wouldn't be anywhere near my ballpark. It would be 0.00 something something. You'd catch that mistake. All right, let's see if you can work one. I don't like that one. Let's go clear to... let's do this one. Okay, so it says, I gotta make it so the screen can read it. It is estimated that 8.3% of all Americans have diabetes. Okay, so my number earlier was way off. That's all right. There, is that still readable? Okay. So it's estimated that 8.3% of all Americans have diabetes. Suppose that a random sample of 74 is taken. What is the probability that the proportion of people in the sample who are diabetic differs from the population proportion by less than 1%? Work that problem. I'll come around and check on you. Don't be writing your English paper. That's not, X, remember, is the number of successes. This is the proportion, right? It will differ by no more than 1%. So, but that's actually not the proportion either. It says differ by more than 1%. So differ by no more than 0.01. So it's 0.083. What's different by 0.01 from that? See what I mean? Good. So that's your lower bound. And then you could be 1.01 above it, and your upper bound. Right? Looking at what that means, this number is confusing. P is 0.083, right? P hat is X over N. X is number of successes, right? So X is P times the 74. So that's the mean of the X's. But I actually wouldn't even mess with that. You don't need it. You just need P hat. So you figure out if you're going to be off from this value by no more than 1%, that's 0.073 to 0.09. So figure out, so those are your P hats. Okay, you're making this exact same mistake that she made, and I've seen two others make that mistake. So, yeah, you're doing the same thing. This one is a little bit tricky, so let me stop you if you're already going along. I'm seeing an awful lot of people say that X is 0.01. X is not 0.01. It says the probability that the proportion of people who are diabetic differs from the population proportion by less than 1%. So let's do the given thing again, right? What have we been given? Okay, P is 0.083, right? N is 74. And then all that they've given it, the only other number in there is this 1%. But what is that number?
What's your bound?
It's the bound. Differs from by less than that. Differs from the population proportion, right? Differs from the population proportion. So what's differing by 1% from this? Now, they're good here with trying to trick you, because they give you a percent here, but a proportion or a percent here. Down here they talk about proportions. So you have to convert this to a proportion. What is 1%? 0.01. So what's differing from P by 0.01? P hat is, let me scoot this over. P hat is less than or equal to 0.073 to 0.093. Isn't that being 0.01 away from here?
Why did this be X and then you got this something?
You don't need X even for this problem. The only thing you need to do with X is determine whether you've got enough successes and enough failures to make this work. Okay? But the central limit theorem works with p hats. So you don't really even need to go to the x's. Does everybody understand this? That's what that statement is giving me. It's saying I want the probability of being between 0.073 and 0.093. Everybody get that? All right. So that 0.01, people were trying to use the 0.01 as an x or as a p hat or whatever. It's not p hat, it's not x. It's telling you how to get to p hat, but you got to do a little fiddling with it to get there. Okay, keep going. You got a question?
Yeah.
Okay.
You said X is not real.
Right. I also said you don't really even need x. You just need p hats. The formula for standard error doesn't have x in it. It's got p. Standard error p hat. Right? Okay, that's right. Okay. So then now you can draw your picture and use that standard error to figure out where 0.073 and 0.093 are, and then you'll be able to go right to your normal CDF. You just study your 0.01. 0.01 is out of the picture, right? We use the 0.01 to give us the 0.73 and the 0.093. But, so the 01 is, we're done with it. You don't need that one for anything. Draw me a picture. Okay. How far out with those dotted lines? That's not what's under the dotted line. That's what we want the probability for, but we got to first figure out where that number goes by figuring out the dotted line. So how far out does the dotted line go? One standard error, each stretch. So hence, you need to first get the standard error. And then that'll tell you what numbers go under your dotted line. Then you figure out where these two numbers go in relation. That looks right. Yep. Difference by less than. Right? It says, this time it says difference by less than. You shaded more than. Those numbers are not standard. They're not related to variability. It's your standard error. I actually don't know the answer, but that looks in the ballpark. The problem I have with your picture is you didn't draw the dotted line at plus or minus 1 standard error, so I don't know whether these are relatively correct position or not. But I know what the real picture looks like. Yeah, it shouldn't be. Oh, you put 0.83, not 0.03. That was better. Yeah, that's right. Yeah. Okay, I've only got 1 minute left, so I'm going to finish it out for you, and I've done it on the slides already. So, you've already done all this, but by subtracting 0.01 and adding 0.01 to the population proportion, we know that we want the area between 0.73 and 0.93. All right, so we got that far. And then the standard error, let me just widen this a little bit. The standard error you all were getting 0.03207. So then you draw the picture. You anchor the picture with your standard error line, the 032 whatever, out. And then the 073 and 093 you can see then are really pretty darn close to the middle. So the region in between is shaded. So the ballpark estimate of that is probably around 20%, 0.2. And there's the answer. Okay, so you do normal CDF, 0.7073, 0.093, mean of 0.083, and then this big long nasty expression for the standard error, but I would just enter the 0.03, whatever it was, 207 or whatever. As long as you enter enough decimal places of accuracy, you should get that same number too. Say that again.
0.115.
Yeah, 0.1.
0.05.
There.
By adding the fact that the standard error from